Okay, y'all, I just wanted to give us another review problem that we can work with from section 3.3 since it is one of the more confusing sections with word problems. So the example I wanted to pick out was number 17. It's not on your homework, but it's in the same section. It's section 3.3, number 17, and it's found on page 272. So the problem reads this. An orchard presently has 30 trees per acre. Each tree yields 480 peaches. It is determined that for each additional tree that is planted per acre, the yield will be reduced by 12 peaches per tree. How many trees should be added per acre to maximize the yield? So you can kind of see that I summarized the situation up right here. Currently, we have 30 trees per acre. That's what we're sitting at. And currently, we're making about 480 peaches per tree. Now, if we want to add trees, what's going to happen is that each tree is going to reduce that 480 by 12 for each tree we add. And the reason might be, not enough room for roots, I don't know. But for each tree we plant per acre, every tree gets reduced by 12 peaches per tree. Now we're asking how many trees should be added, not total, how many trees should be added per acre to maximize the yield. So, first step, remember, read the problem, summarize it, we've already done that. Second step, find out what we're after. How many trees should be added per acre? Okay, so we're after this. Step number 3, figure out the function that's going to help us. Usually that's the function that's coupled up with either the word maximize or minimize. So we're trying to maximize yield in this question. So that being said, I'm going to go ahead and start by trying to make a yield function. Now, I don't try to dive right into just whatever. I try to start really broad. So the first thing I'm going to start with is, what's yield? Well, I guess it's amount of trees times the number of peaches they produce. It's kind of like a revenue function. From here, I'm going to go ahead and try to fill in what trees are and what number of peaches per tree would be. Yet again, we see a situation kind of like that one problem in class where if we increase, something happens. So I'm going to go ahead and introduce a variable for us. I'm going to write it in blue, that way it stands out. Let's call it I. And I will be number of increases. Think about it as kind of the amount of trees we're actually adding, right? So if I is 1, we just added 1 tree per acre. This is going to help give me language to talk about these two things. For instance, the amount of trees. Yet again, in these situations, just like a revenue problem, think about your base case, or currently, and then think about the adjustment. So the amount of trees currently, or in our base case, is 30. And we're talking per acre, so I should say that. If that's cut off, I'm sorry. I'm not shooting with a wide angle lens. So currently we have 30 trees per acre. Now, when we adjust, if we were to adjust, I guess we're only adding 1 tree every single time we adjust. So the amount of trees better be something like 30 plus I. Now, going over here to the number of peaches per tree. Yet again, base case and then the adjustment. So the base case is we have 480 per tree. Now the adjustment, I guess we lose 12 every single time we add 1. So since we're losing, it better be a minus. And then since we're adding, since we're losing where it's a minus, we better include I in there. We're losing 12 each time, so we end up with a 12I. And that's going to be my function. That's going to help me out. One thing we can do is potentially simplify. So if I may whip out my Steve Jobs calculator, nothing scripted, this is exactly how I'd solve it. I guess we'd have that 30 times 480 is 14,400 plus 480i minus 12 times 30 is 360i. And then last but not least, minus 12i squared. Or if we simplify, 14,400 plus 480 minus 360, 120 I, and then minus 12i squared. The reason we're trying to go after this, remember, is because we're maximizing the yield. Since we're maximizing, that leads us to want to do a 3.1 or a 3.2 process to figure out where the maximum of this function occurs. So that's the reason we're going for it. Now that we're here, if we figure out where a maximum happens at, we'll be able to get our hands on the amount of trees that we should add. So from there, I'll call it y. If we find our derivative, I'll guess we'll end up at 120 minus 24i. We go ahead and solve for the critical point since we're looking for a maximum. So the 3.3 process was this part right here. Now we're in a 3.1 or a 3.2 problem. So look for your critical points. Set it equal to 0. Add over the 24i. And I'm going to take this right here, if I may. And what we can say then, 120 divided by 24 is just 5. I'll draw a little border right in here, kind of help us out. So I better equal 5. Now how do we know that's an actual maximum? Good question. We can either do the first derivative test or we can do the second derivative test. If we do the second derivative test, which I'll go ahead and box in green right in here, that arrow is a little confusing. I'll go ahead and box the second derivative right here, y double prime. That's just negative 24. So that means when we plug in 5, we're getting a negative number. You're concave down, meaning you really have a maximum. So this thing right here is just a big check. That's what we're doing. Check mark. So that tells me now that if I increase by 5, I truly do end up at a maximum. So I'll come back over here and write out my final answer with all that work being shown. Hey, we should add 5 trees per acre. And that should do it for us.